Is this working? All right. Oh. Yeah, welcome to another live stream of reading a paper. I don't have that much time, so I will just quickly gloss over what we did the last. Yesterday we were not online, but the days before we were looking into graph neural networks, into how these architectures aggregate neighborhoods in a message passing algorithm into their node representations, and how they get a graph representation from these node representations out of it. And most notably, you in the end have a vector for each of the nodes in the graph, or the vertices, and at some point you have to do a readout if you want to perform a classification or regression on the entire graph. And one of those papers used something called set to set. And there are different architectures that deal with extracting or performing some learning task on set data. And for this specifically, the set we work on is a set of nodes of a graph. And I was looking for a paper and came across this one here, which was widely cited. It is, you can find it here. It's also published in the proceedings of NeurIPS, which is, Neural Information Processing Systems. So if you want to read it, for yourself, you can find it on arXiv as well. The PDF is here. The link is also in the description. Let's get started. I pulled up our node and I will just start. So again, like always, we start with the abstract. We look at the introduction. We then look at the structure of the paper, gloss over it. We read the conclusion, and then we will do a second pass probably, where first we look also at the references, but we're probably just glossing over them. And then we do a second pass where we also read the entirety of the other content, except all of the appendices, and maybe not get into detail in regard to every last bit that is mentioned in here. So let's get started. Deep Sets by Manzil, Zaheer, Satwik, Couture, and so on, from the Carnegie Mellon University and Amazon Web Services. Okay. Carnegie Mellon University. All right. So, abstract. We study the problem of designing models for machine learning tasks defined on sets. In contrast to the traditional approach of operating on fixed dimensional vectors, we consider objective functions defined on sets that are invariant to permutations. Such problems are widespread, ranging from estimation of population statistics to anomaly detection in piezometer data of embankment dams to cosmology. Our main theorem characterizes the permutation invariant functions and provides a family of functions to which any permutation invariant objective function must belong. This family of functions has a special structure which enables us to design a deep network architecture that can operate on sets and which can be deployed on a variety of scenarios, including both unsupervised and supervised learning tasks. We also derive the necessary and sufficient conditions for permutation equivariance in deep models. We demonstrate the applicability of our method on population statistic estimation, point cloud classification, set expansion, and outlier detection. Okay, so the basic problem they are tackling is the following. So in traditional ML, the traditional approach is, okay, you have a feature vector, x1, x2, x3, x4, and so on. Well, let's do it a little bit differently. x1, x2, dot, 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 xn. So you have this n-dimensional feature vector, and then you define a multi-layer perceptron that uses these n features and then processes it into an output that also is has some dimensionality. Now, for example, in our graph, we don't know how many of these features, let's say, we have. So, for example, we could have 10 nodes where each node has like 10 different features. So we have 100 features, if you will so. And we can also have an instance where there's more than 10 nodes or less than 10 nodes. And this is obviously a problem for for MLPs that rely on a specific amount of features. Now, the next problem we have is that, well, in a graph, if we have multiple nodes, vertex 1, vertex 2, vertex 3, for example, and they all have these hidden states, we can consider this, but we can also consider a different permutation of this. So for example, HV2 is first, HV1, and HV3. And these two, they have the same meaning. Mean the same. Or order does not matter. We want the neural network to have any sort of permutation of these, which is a 3 factorial. So there are 3 factorial permutations, and we want for all of them the same output. So same output. And as you can imagine, if we train an MLP and we just concatenate these 3 together, the MLP will probably not be able to be permutation invariant per se. Now, if you have a lot of data, it might be able to learn something approximate to this, but by design it is not permutation invariant. What they mean by permutation equivariant, I don't really know. They probably will explain this, hopefully. But okay, so, and what they are now doing is, okay, let's define functions that are permutation invariant, and what they probably do in step 2 is show that propose a new architecture, and third, prove that the new architecture is such a function. All right, so we'll probably see this in the introduction again, but let's continue. So, introduction. A typical machine learning algorithm like regression or classification is designed for fixed dimensional data instances. They're extensions to handle the case when the inputs or outputs are permutation invariant sets rather than fixed dimensional vectors is not trivial, and researchers have only recently started to investigate them. In this paper, we present a generic framework to deal with a setting where input and possibly output instances in a machine learning tasks are sets. Similar to fixed dimensional data instances, we can characterize two learning paradigms in case of sets. In supervised learning, we have an output label for a set that is invariant or equivariant to the permutation of set elements. Examples include tasks like estimation of population statistics, where applications range from gigascale cosmology to nanoscale quantum chemistry. Next, there can be the unsupervised setting, where the set structure needs to be learned. For example, by leveraging the homophily-heterophily tendencies within sets. An example is the task of set expansion, also known as audience expansion, where given a set of objects that are similar to each other, for example, a set of words, lion, tiger, leopard, our goal is to find new objects from a large pool of candidates such that the selected new objects are similar to the query set. For example, find words like jaguar or cheetah among all English words. This is a standard problem in similarity search and metric learning, and a typical application is to find new image tags given a set of possible tags. Likewise, in the field of computational advertisement, given a set of high-value customers, the goal would be to find similar people. This is an important problem in many scientific applications, for example, given a small set of interesting celestial objects, astrophysicists might want to find similar ones in large sky surveys. And here we also see the connection to Amazon. More or less? Finding high-value customers? Or what? Okay. Main contributions. In this paper, 1, we propose a fundamental architecture, deep sets, to deal with sets as inputs and show that the properties of this architecture are both necessary and sufficient. We extend this architecture to allow for conditioning on arbitrary objects. And 3, based on this architecture, we develop a deep network that can operate on sets with possibly different sizes. We show that a simple parameter sharing scheme enables a general treatment of sets within supervised and semi-supervised settings. Finally, we demonstrate the wide applicability of our framework through experiments of diverse problems. Okay, so what they do is they want a network architecture that is either permutation invariant, that is, if you have different permutations, you get the same output, or permutation equivariant, so if you permute the set, you also get a output change that is more or less desired, or that fits the rearrangement in the input. One easy thing I could imagine is that, for example, for all of these, because they mention parameter sharing, we had multiple vectors, HV1, HV2, HV3, or let's, yeah, HVN, the number of nodes. And we said, okay, we don't know how many of these there are in the set, so we can't really have a single multi-layer perceptron that they just takes all of them and processes them, because the dimensionality is not known. So what we can do instead is take an MLP that takes in one node at a time. So the MLP, let's do it like this, takes in this, and this, and it produces an output for each and every one of them. So all of these nodes share the same multi-layer perceptron and the same computation. And then we have HV1 prime, HV2 prime, HV3 prime, and HVN prime. And now what we can do is we add an aggregation layer. And we take in all of these, oops, and somehow aggregate them together. And then we produce an output. And this is probably, we can use a sum, a mean, or whatever in the aggregation. And this is the parameter sharing part. Well, but let's see how they do it. Okay, so they briefly introduce permutation invariance and equivariance. The structure of functions on sets, related results, Definetti theorem, which I'm not familiar with. Representer theorem and kernel machines. Okay, spectral methods. Deep sets, the architecture. So this is their architecture proposal. This was more the formal framework. So this is more like this first thing is the formal framework for functions on sets. And then we have the architecture that is proposed, and probably some experiments, other related works, applications and empirical results. So they test this architecture. Set input scalar response. Supervised learning to estimate population statistics. Sum of digits. image, point cloud classification, improved redshift estimation using clustering information, set expansion, conditioning, text concept set retrieval, okay. Methods, evaluation, result and aggregation, image tagging, and set anomaly detection. And then the summary. Oh, we haven't read the summary. Okay, yeah. So let's read the summary. In this paper, we developed deep sets, a model based on powerful permutation invariance and equivariance properties, along with the theory to support its performance. So as we already saw with many of the previous advances in the field, you always start with a theoretical framework for assessing the representative power of your architecture, and then you show that the architecture you use follows this formal framework, and then you test it, and that's it. You test it, see it works. Okay, it works better than the ones that don't follow the framework, and corroborate your hypothesis. Now, what is the summary for this? A model based on powerful permutation invariance and equivariance properties, along with theory to support its performance. We demonstrate the generalization ability of deep sets across several domains by extensive experiments and show both qualitative and quantitative results. In particular, we explicitly show that deep sets outperform other intuitive deep networks which are not backed by theory, which is exactly what I said. Okay. Last but not least, it is worth noting that the state-of-the-art we compare to is a specialized technique for each task, whereas our one model, i.e. deep sets, is competitive across the board. Okay, this sounds very nice. Let's start with their formal framework. Permutation invariance and equivariance. Problem definition. So a function f transforms its domain x into its range y. Usually, the input domain is a vector space Rd, and the output response range is either a discrete space, example given the set of 0 and 1, in case of classification, or a continuous space R in case of regression. Now, if the input is a set, x is equal to x1, the set of x1 to xm, where xm is this back letter x, i.e. the input domain is the power set x is equal to 2 to the back letter x, then we would like the response of the function to be indifferent to the ordering of the elements. In other words, the power set xm elements. Okay, let's not get hung up with the formulas here, but okay. Then we would like a function f 2 to the back letter x maps to y, acting on sets must be permutation invariant to the order of objects in the set, i.e. for any permutation f of x1 to xm, and then they introduce the pi here, they're equal. So whether we have this permutation here, v1, v2, v3, or v2, v1, v3, we expect the same output, which is permutation invariance. Now, on the other hand, in the supervised setting, given n examples of x1 to xn, as well as their labels y1 to yn, the task would be to classify regress with variable number of predictors while being permutation invariant with respect to predictors. Under unsupervised setting, the task would be to assign high scores to valid sets and low scores to improbable sets. These scores can then be used for set expansion tasks such as image tagging or audience expansion in field of computational advertisement. In a transductive setting, each instance xmn has an associated label ymn. Then the objective would be instead to learn a permutation equivariant function that upon permutation of the input instances permutes the output labels for any permutation. Yes. Okay, so whenever so let's say we have v1, v2, v3, and we put them into the set architecture. Set network. We get an output. We get one output, which is either a probability or a real valued value for regression. And when we have v2, v1, v3, and we put it through the set network, so this is now a different order. Those two are swapped. We want to get the same y. This is permutation invariance. Now, if we, for example, have a network that predicts for each node, set network that predicts for each node a different value, and we permute the set, we also want the output to be permuted. Right? So if these two swap, then these two swap as well in the output. Okay. Permutation equivariance. All right. We want to structure. We want to study the structure of functions on sets. Their study in total generality is extremely difficult, so we analyze case by case. We begin by analyzing the invariant case, when backladder x is a countable set and y is equal to r. Where the next theorem characterizes its structure. Theorem 2. A function f of x operating on a set x, having elements from a countable universe, is a valid set function, i.e. invariant to the permutation of instances in x, if and only if it can be decomposed in the form the letter rho, which is probably the network or the function. And then for each x and x, 5x, for suitable transformation, phi and rho. So we go through all of the instances, apply a function, and then we somehow aggregate them. So as I said before, we have first element-wise function, which is denoted as phi, and then we have the aggregation function. Rho. The extension to they always leave out the. The extension to the case when x is uncountable, like x is equal to r, we could only prove that f of x is equal to this, holds for sets of fixed size. The proofs and difficulties in handling the uncountable case are discussed in Appendix A. However, we still conjecture that exact equality holds in general. Next, we analyze the equivariant case when x is equal to y is equal to r, and if f is restricted to be a neural network. A neural network layer. The standard neural network layer is represented as, holy man, what is this letter? I don't remember. F of x is equal to sigma of, yeah. Let's look it up. Greek letters. It is theta, the big theta. Okay. Where theta is a matrix in R, m by m, is a weight vector, and sigma maps R maps real values to other real values is a non-linearity such as sigmoid function. The following lemma states the necessary and sufficient conditions for permutation equivariance in this type of function. Lemma 3, the function f theta defined above is permutation equivariant if and only if all the off-diagonal elements of theta are tied together and all the diagonal elements are equal as well. That is, theta is equal to lambda times the identity matrix plus gamma okay, so this is 1, 1, 1, 1, 1 transposed. All right, and I is the identity matrix. So if gamma times a 1 vector times a 1 vector transposed, which is then also an m by m matrix, right? This result can easily be extended to higher dimensions when lambda and gamma can be matrices. Okay. Related results. The general form of Theorem 2 is closely related with important results in different domains. Here we quickly review some of these connections. De Finetti theorem. A related concept is that of an exchangeable model in Bayesian statistics. It is backed by the De Finetti's theorem, which states that any exchangeable model can be factored as this, where theta is some latent feature and alpha and m0 are the hyperparameters of the prior. To see that this fits into our result, let us consider exponential families with conjugate priors where we can analytically calculate the integral of 2. In this special case, blah blah blah. Now if we marginalize out theta, we get a form which looks exactly like one in Theorem 2. Okay, let's not go into this in detail, because I would probably not understand it at this point. Representative theorem and kernel machines. Support distribution machines use f of p is equal to all of this as a prediction function. where pi and p are distributions and alpha and b are real values. In practice, the p distributions are never given to us explicitly, usually only identically and independently distributed sample sets are available from these distributions. And therefore we need to estimate kernel k blah blah blah. A popular approach is to use this kernel where k is another kernel operating on the samples. Now these prediction functions can be seen fitting into the structure of our theorem. I have no idea what they were even trying to do with this, but whatever. Spectral methods. A consequence of the polynomial decomposition is that spectral methods can be viewed as a special case of the mapping rho and phi of x. In that case, one can compute polynomials, usually only up to a relatively low degree, such as k is equal to 3, to perform inference about statistical properties of the distribution. The statistics are exchangeable in the data, hence they could be represented by the above map. Alright, so let's get into the meat of this paper, which is, yeah, I mean, the formal framework is probably also the meat, but let's look at the architecture, the practical stuff. So architecture, invariant model. The structure of permutation invariant functions in Theorem 2 hints at a general strategy for inference over sets of objects, which we call deep sets. Replacing phi and rho by universal approximators leaves matters unchanged, since, in particular, phi and rho can be used to approximate arbitrary polynomials. Then, it remains to learn these approximators, yielding in the following model. Each instance xm is transformed, possibly by several layers, into some representation phi xm. The representations phi xm are added up and the output is processed using the rho network in the same manner as in any deep network. Okay, so there's even more. So they add them up. So this is plus, and then they have another network that maps the output. So then we have maybe an MLP here, and then we get the output. And this is their thing. So, and this is for the invariant model, right? So summing is for invariant models. Pooling sum for invariant. And let's see what they do for the, no, let's first read the rest. The representations phi xm are added up and the output is processed using the rho network in the same manner as in any deep network. For example, fully connected layers, nonlinearities, etc. Optionally, if we have additional meta information z, then the above mentioned networks could be conditioned to obtain the conditioning mapping phi xm given z. In other words, the key is to add up all representations and then apply nonlinear transformations. Equivariant models. So we could also condition this on other variables. So here we could also put in a z and then condition this network. No. We could also put the z in here, right? Or where did they put the z? On the phi network. Yeah. But you could also put the z somewhere else. So let's just delete that for now. Okay. Equivariant model. Our goal is to design neural network layers that are equivariant to the permutations of elements in the input x. Based on lemma 3, a neural network layer f theta of x is permutation equivariant if and only if all the off-diagonal elements of theta are tied together and all the diagonal elements are equal as well, i.e. theta is equal to lambda times the identity matrix plus gamma times one vector times the one vector transposed. For lambda and gamma element R. This function is simply a nonlinearity applied to a weighted combination of 1, its input, the identity matrix times x, and 2, the sum of input values. The sum of input values. So if we have a vector wait. Good afternoon. Okay, so the one vector, oops. Right, is this, and then the one vector times the one vector transposed is just the matrix, right? But now, if we have an input x, that is a 4x1 now. So this is x1, x2, x3, x4. Then we get the x1, 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 x1 plus x2, 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 x2 plus x3, x3, blah, blah, blah. And then we get a matrix x1 plus x2 plus x3 plus x4. x1 plus x2 plus x3 plus x4. x1 plus x2 plus x3. Is this correct? This would be the sum of the elements, but also just repeat it. So the sum of input values. Wait. Why do they need this? They could just... Or do they do it differently? Or is X also a matrix? Well, okay, let's just trust them. Let's not get lost in the details. Since summation does not depend on the permutation, the layer is permutation equivariant. We can further manipulate the operations and parameters in this layer to get other variations. For example, this. Okay, so the identity matrix times a gamma. So this function is a weighted combination of its input and the sum of the input values. Since the summation does not depend on the permutation, the layer is permutation equivariant. Alright, so where the max pooling operation over elements of the set is commutative in practice, this variation performs better in some applications. This may be due to the fact that for lambda is equal to gamma, the input to the non-linearity is max normalized. Okay, I don't quite understand it yet, why this is now permutation equivariant. But okay. So the all ones vector. Okay. Okay, other related works. Several recent works study equivariance and invariance in deep networks with respect to general group of transformations. For example, 15 construct deep permutation invariant features by pairwise coupling of features at the previous layer, where this is invariant to transposition of I and J. Pairwise interactions with insets have also been studied in these works. 18's approach unordered instances by finding good orderings. What? The idea of pooling a function across set members is not new. In 19, pooling was used binary classification tasks. Man, there are some errors in here. Pooling was used for the binary classification task for causality on a set of samples. 20 uses pooling across a panoramic projection of 3D objects, or of a 3D object for classification, while 21 performs pooling across multiple views. Yeah, whatever. In light of these related works, we would like to emphasize our novel contributions. 1. The universality result of Theorem 2 for permutation invariance that also relates deep sets to other machine learning techniques, see section 3. And 2. The permutation equivariant layer of 4, which according to lemma 3 identifies necessary and sufficient form of parameter sharing in a standard neural layer. And 3. Novel application settings that we study next. Okay, let's look at the graphs. Population statistic estimation. Top set of figures show prediction of deep sets versus an SDM, whatever the SDM is in this case. For n is equal to 2 to the 10 case. Okay. I have no idea what this tells us. number of set examples, and mean squared error. Okay. Applications and empirical results. Represent a diverse set of applications for deep sets. For the supervised setting, we apply deep sets to estimation of population statistics, sum of digits, and classification of point clouds, and regression with clustering side information. The permutation equivariant variation of deep sets is applied to the task of outlier detection. Finally, we investigate the application of deep sets to unsupervised set expansion, in particular, concept set retrieval and image tagging. In most cases, we compare our approach with the state of the art and report competitive results. Set input scalar response, supervised learning, learning to estimate population statistics. In the first experiment, okay. In the first experiment, we learn entropy and mutual information of Gaussian distributions without providing any information about Gaussianity to deep sets. The Gaussians are generated as follows. Rotation, we randomly choose a 2x2 covariance matrix, sigma, and then generate n sample sets from a normal distribution of size blah for n random values. Our goal was to learn the entropy of the marginal distribution of first dimension. R of alpha is the rotation matrix. Correlation, we randomly choose a d by d covariance matrix. Sigma for d is equal to 16, and then generate n sample sets from this of size m is equal to this, blah, blah, blah. Yeah. We train using L2 loss with a deep sets architecture, having 3 fully connected layers with ReLU activation for both transformations, sigma, phi, and O. We compare against support distribution machines using an RBF kernel and analyze the results in figure 1. Okay, sum of digits. Next, we compare to what happens if our set data is treated as a sequence. We consider the task of finding sum of a given set of digits. We consider 2 variants of this experiment. Text, we randomly sample a subset of a maximum m is equal to 10 digits from this dataset to build 100k sets of training images where the set label is sum of digits in that set. A maximum digits from this dataset where the set label is sum of digits in that set. We test against sums of m digits for m starting from 5 all the way to up to 100 over another 100,000 examples. Image. MNIST8M contains 8 million instances of 28 by 28 grayscale stamps of digits in 0 through 9. We randomly sample a subset of maximum m is equal to 10 images from this dataset to build n is equal to 100k sets of training and 100k sets of test images. So they just take 10 images with numbers and they feed it through their set network, deep sets architecture, and then they predict the sum of these digits, which is interesting. And then they compare this against an LSTM and gated recurrent unit. Okay. Point cloud, okay, they also had a chart here, right? Sum of digits to add. So accuracy of digit summation with text. All operators are trained on tasks of length 10. Okay. Oh, okay. They trained on length 10 and then they tested on larger amounts as well. So, and we see the deep sets architecture generalizes a lot better. Deep sets better or performs better in out of distribution tests. And we see again that these people use out of distribution tests to make some statements about how well does this generalize. Generalizability. Point cloud classification. A point cloud is a set of low-dimensional vectors. Okay? This type of data is frequently encountered in various applications like robotics, vision, and cosmology. In these applications, existing methods often convert the point cloud data to voxel or mesh representation as a pre-processing step. For example, this works. Since the output of many range sensors, such as LiDAR, is in the form of point cloud, direct application of deep learning methods to point cloud is highly desirable. Moreover, it is easy and cheaper to apply transformations such as rotation and translation when working with point clouds than voxelized 3D objects. As a point cloud data is just a set of points, we can use deep sets to classify point cloud representation of a subset of shaped net objects called model net 40. This subset consists of 3D representation of training and test instances belonging to 40 class of objects. Each set is normalized by the initial layer of the deep network to have zero mean and unit global variance. And they also show the performance on these, on variational autoencoder. Okay, so they are worse than instance size. 5,000 by 3. 32 by 3. Okay. Improved redshift estimation using clustering information. Important regression problem in cosmology is to estimate the redshift of galaxies corresponding to their age as well as their distance from us. Based on photometric observations, one way to estimate the redshift from photometric observations is using a regression model. On the galaxy clusters, the prediction for each galaxy does not change by permuting the members of the galaxy cluster. Therefore, we can treat each galaxy cluster as a set and use deep sets to estimate the individual galaxy redshifts. I think, okay. Okay, they show that their deep sets architecture is also great here. Let's look at set expansion. In the set expansion task, we are given a set of objects that are similar to each other, and our goal is to find new objects from a large pool of candidates such that the selected new objects are similar to the query set. To achieve this, one needs to reason out the concept connecting the given set and then retrieve words based on their relevance to the inferred concept. It is an important task due to a wide range of potential applications, including personalized information retrieval, computational advertisement, tagging large amounts of unlabeled or weakly labeled datasets. This sounds very scary. Going back to De Finetti's theorem in section 3.2, where we consider the marginal probability of a set of observations, the marginal probability allows for very simple metric for scoring additional elements to be added to X. In other words, this allows one to perform set expansion via the following score. So the score of observing X given the rest of the set is the logarithm of the probability of combining X and of adding X to X given alpha, whatever alpha is, minus the logarithm of the probability of observing X giving alpha times the probability of observing the instance X given alpha. And note that the score is the pointwise mutual information between X and X. Moreover, due to exchangeability, it follows that regardless of the order of elements, we have this. Okay, we will not go into the details here, but I wonder how they actually train the network. When inferring sets, our goal is to find set completions. These for an initial set of query terms, such that the aggregate set is coherent. This is the key idea of the Bayesian set algorithm. Using deep sets, we can solve this problem in more generality, as we can drop the assumption that of data belonging to a certain exponential family. For learning the score, we take recourse to large margin classification with structured loss functions to obtain the relative loss function, a loss objective. Okay. In other words, we want to ensure that the score of observing the small x given X is greater than or equal to observing X prime in X plus a delta whenever X should be added and X prime should not be added to X. Okay, and the large margin is basically the delta. Conditioning. Often machine learning problems do not exist in isolation. For example, tasks like tag completion from a given set of tags is usually related to an object Z, for example an image that needs to be tagged. Such metadata are usually abundant. For example, author information in case of text, contextual data such as the user click history, or extra information collected with LiDAR point cloud. Conditioning graphical models with metadata is often complicated. For instance, in the beta binomial model, we need to ensure that the counts are always non-negative regardless of Z. Fortunately, deep sets does not suffer from such complications, and the fusion of multiple sources of data can be done in a relatively straightforward manner. Any of the existing methods in deep learning, including feature concatenation by averaging or by max pooling, can be employed. Incorporating these metadata often leads to significantly improved performance, as will be shown in experiments in section 4.2.2. Okay, text concept set retrieval. In text concept set retrieval, the objective is to retrieve words belonging to a concept or cluster given few words from that particular concept. For example, given set of words tiger, lion, cheetah, we would need to retrieve other related words like jaguar, puma, etc., which belong to the same concept of big cats. This task of concept set retrieval can be seen as a set completion task conditioned on the latent semantic concept and therefore our deep sets from a desirable approach. The dataset. We construct a large dataset containing sets of 50 related words by extracting topics from latent Dirichlet allocation taken out of the box. Okay, to compare across scales, we consider three values of k given us three dataset LD methods. We learn this using a margin loss with deep sets architecture having 3 fully connected layers with relu activation for both transformations phi and rho. Details of the architecture and training are in Appendix E. We compared several baselines. A random picks a word from the vocabulary uniformly at random. Base set and W2 V near computes the nearest neighbors in the word to vec space. Note that both base set and W2 word to vec neural network are strong baselines. The former runs Bayesian inference using beta binomial conjugate pair, while the latter uses the powerful 300-dimensional word to vec trained on the billion-word Google News corpus. Okay. Evaluation, we consider the standard retrieval metrics, recall K, median rank, and a mean reciprocal rank for evaluation. To elaborate, recall at K measures the number of true labels that were recovered in the top K retrieved words. We use 3 values of K. The other 2 metrics, as the name suggests, are the median and mean of reciprocals of the true label ranks, respectively. Each dataset is split into train, val, and test. We learn models using train and evaluate on test, while val is used for hyperparameter selection and early stopping. Makes sense? As seen in Table 3, our deep sets model outperforms all other approaches on the other datasets by any metric, highlighting the significance of permutation invariance property. Our model does not perform well when compared to word to vec near. What? Okay. We hypothesize that this is due to small size of the dataset insufficient to train a high capacity neural network, while word to vec near has been trained on a billion word corpus. Makes sense? Nevertheless, our approach comes the closest to word to vec near amongst other approaches. Okay. Well, could you just use the word to vec as an embedding and then put the deep sets architecture on it? You could do that. What if we apply the deep sets architecture on the word to vec embeddings? I suspect that it gets better. Image tagging. We next experiment with image tagging, where the task is to retrieve all relevant tags corresponding to an image. Images usually have only a subset of relevant tags. Therefore, predicting other tags can help enrich information that can further be leveraged in a downstream supervised task. In our setup, we learn to predict tags by conditioning deep sets on the image, i.e. we train to predict a partial set of tags from the image and remaining tags. At test time, we predict tags from the image alone. We report results on the following 3 datasets. So the set is the output, right? They're just one image. And then at test, note that a particular baseline does not do as well as yes. Likely because the dataset is too small to train a high capacity neural model from scratch, whereas word to vec was pre-trained on a billion word corpus. Even so, their approach comes within 0.5 of it on recall at 10. Yeah, so this was also what they were saying, right? So, but I suspect that if you use the word to vec embeddings, that Yeah, that their approach, that using the architecture on top of it would greatly improve it. But yeah, which table was it? So, table 3. Man. Yeah, okay, where to back? Yeah. Yeah, recall at 10. And 10 was the size of the set, right? Yeah, yeah, okay. Interesting. Okay. Um, where was I? Okay. In our setup, we learn to predict tags by conditioning deep sets on the image, i.e. we train to predict a partial set of tags from the image and remaining tags. At test time, we predict tags from the image alone. So what I suspect is that they just, at test time, start with an empty set and then predict tags and just use the image, and at train time, yeah, I don't really know how they do it, but okay. We report results on the following 3 datasets: ESP game, IAPRTC, whatever, Goku tag. We refer the reader to Appendix F for more details about the dataset. Yeah, okay, we would have to read that. The setup for deep sets to tag images is similar to that described in section 4.2.1. The only difference being the conditioning on the image features, which is concatenated with a set feature obtained from pooling individual element representations. Okay, so what they do is they have a set of tags. Oops. And for each tag, they process them individually with their, I don't know what they use here. Some, let's call it layers. Then they get a refined representation for each and, or they get a representation for each and every one of them. Then they pool them together. Pooling. And here they have the image. They probably put a CNN on it. And then they, so this is the pooled representation or whatever. And then they concatenate these two. And then they predict the likelihood of, or they predict the score of, no. Actually, how do they do this? They, well, okay. I'm unsure. Let's put a question mark here. How do they predict the scores for each and every one? For an initial set of query terms, okay. So they probably just predict the probabilities for all of the completions, but do they also condition it on the completions? I don't know. Would be interesting to see how they did it. But then here they probably output scores. Scores. No. They have more layers. And then they get the final score. But whether they just predict a fixed vector that is the set completion vector, or whether this is something else, I don't really know. Okay. Their evaluation. Okay, we follow the evaluation metrics as in this. What is 44? Discriminative metric learning and nearest neighbor models for image auto annotation. Okay. Precision, recall F1, and number of tags with non-zero recall. Okay. These metrics are evaluated for each tag, and the mean is reported. For Coco tag, however, we use recall at k for 3 values of k, 100, 10, 100, and 1000, along with median rank and mean reciprocal rank. Okay. Black hair and rosy cheeks. Okay. Each row shows a set constructed from celeb A dataset, such that all set members except for an outlier share at least 2 attributes on the right. The outlier is identified with a red frame. The model is trained by observing examples of sets and their anomalous members. And their anomalous members without access to the attributes. The probability assigned to each member by the outlier detection network. Okay, so this is outlier detection. This is something else. Results and observations. This is now for the image tagging, right? Okay, table 4. Oh, these are pretty low scores, but I don't know what this kind of. Is it the traditional precision and recall, or is it not? Because if it is, it's pretty low. But maybe it's also because it's yeah, actually not that easy. Oh. Okay. Okay, so now their interpretation of the results. Results of image tagging on ESP Game and IAPRTC in Table 5 on Coco tag. Here are the key observations from Table 4. Performance of our deep set model is comparable to the best approaches on all metrics but precision. Our recall beats the best approach by 2%. On further investigation, we found that the deep sets model retrieves more relevant tags which are not present in list of ground truth tags due to a limited 5 tag annotation. Thus, this takes a toll on precision while gaining on recall, yet yielding improvement on F1. On the larger and richer Coco tag, what? Okay, this is super confusing here, the formatting. We see that the deep sets approach outperforms other methods comprehensively as expected. Okay, yeah, this is significantly better. But okay, why exactly? What is their argument? On further investigation, we found that the deep sets model retrieves more relevant tags, which are not present in list of ground truth tags due to a limited 5 tag annotation. Due to a limited 5 tag annotation. I thought okay. There are only 5 tags in these 2 datasets. And they said, okay, our model retrieves more relevant tags. And yeah. So it retrieves other tags that also apply? Do they mean that? I don't know. Could be. Okay, set anomaly detection. The objective here is to find the anomalous phase in each set. Okay, simply by observing examples and without any access to the attribute values. Celeb A dataset contains 202,599 face images, each annotated with 40 Boolean attributes. We built 18,000 sets of 64 by 64 stamps using these attributes, each containing m is equal to 16 images on the training set as follows. Randomly select 2 attributes, draw 15 images having only those attributes, and a single target image where both attributes are absent. Okay, using a similar procedure, we built sets on the test images. No individual person's face appears in both train and test set. Okay, good. Our deep neural network consists of 9 2D convolution and max pooling layers, followed by 3 permutation equivariant layers, and finally a softmax layer that assigns a probability value to each set member. Note that one could identify arbitrary number of outliers using a sigmoid activation as at the output. Arbitrary number of outliers using a sigmoid activation at the output. Yeah. Arbitrary number of outliers using a sigmoid. Okay, I have to really understand how the equivariant layer works, because okay, it will output some for each of the set members. It will output something. Yeah, how does the permutation equivariant layer work? It was the thing that okay, we will probably have to read that again, but okay. Let's continue. Okay, so they have the softmax and then they assign a probability. What they exactly mean by using the sigmoid activation at the output? Okay, so they mean they apply a sigmoid on each on each of the individual things. Okay, yeah, so what they did is, okay, they had the images and they have one outlier. And then they have their CNN, and then probably each gets processed individually. And then they have their permutation. So let's call it H1, H2, H3, H4, H5. Oops. Equivariant layer that basically mixes the inputs and produces then an output for each and every input, more or less. Okay, and then they take this and apply a softmax. So then you have y1, y2, y3, y4, y5. So all of them get summed together and exponentiated and then divided by the total sum, and then you get, if you add all of them together, this is then just the probability distribution, right? So what's the probability that 1 is the outlier, 2? But what they were saying, okay, this thing can be exchanged with a sigmoid, which is applied on each individual element, and then y1, y2, and so on are between 0 and 1 individually. And this, yeah. Okay, then we have a probability for each element. Makes sense. Our trained model successfully finds the anomalous phase in 75% of test sets. Visually, inspecting these instances suggests that the task is non-trivial even for humans. Okay, see figure 3. Okay, attractive and heavy makeup. What? Well, who decided who's attractive and who's not? That is also an interesting question. But okay. It's pretty crazy that, okay, yeah, black hair. Here, the only one that's blonde. But of course, we also see that. Which one's right? Double chin, wavy hair. Wavy hair? Man, this guy doesn't have wavy hair. What? Wavy hair? Oh man. This is really not easy. As a baseline, we repeat the same experiment by using a set pooling layer after convolution layers. I thought this was... a set pooling layer, okay, and replacing the permutation equivariant layers with fully connected layers of same size, where the final layer is a 16-way softmax. The resulting network shares the convolution filters for all instances within all sets. However, the input to the softmax is not equivariant to the permutation of input images. Permutation and equivariance seems to be crucial here, as the baseline model achieves a training and test accuracy of 6.3%. Okay, so they were using, now not using the permutation equivariant layers, but they were just pooling them together by summing them or something. And then they were just applying a simple, fully connected layer. And it seems that permutation equivariance is important. So, because I did not understand their permutation equivariance layer, I should probably read up again. Okay, so they were saying okay, based on lemma 3. What was lemma 3? Okay, Rm. Next, we analyze the case when and f is restricted to be a neural network layer. The standard neural network layer is represented as f of theta x is equal to sigma of theta times x, where theta is equal to an m by m matrix of real values. Is the necessary and is the weight vector, blah blah blah, is a non-linearity such as a sigmoid function. The following lemma states the necessary and sufficient conditions for permutation equivariance in this type of function. The function f theta defined above is permutation equivariant if and only if all the off-diagonal elements of theta are tied together and all the diagonal elements are equal as well. Okay. Okay. Okay, the transpose. Okay. Let's see. Okay, theta is equal to lambda times the identity matrix plus gamma times the one vector times the one vector transposed. Okay, let's set m equal to 3. Or this was the big M. Then we have theta is equal to lambda times 1, 1, 1. So the identity matrix plus gamma times 1, 1, 1 times 1, 1, 1. Oh man, you see that drift in my writing? It's always there. It's everywhere, this drift. Always drifting to the right side up. but okay. I don't know why I do this. And then you do theta times x, right? Okay, so x is also then just three-dimensional, x1, x2, x3. So what you do is then theta times x is equal to gamma times 1 times x plus gamma times 1, 1, 1, 1, 1, 1. Times x. And then what you get is lambda times, oh, let's write it out. X1, x2. This is so ugly. Whoops. So I times x is x, x1, x2, x3, plus, how do you write a gamma? Whatever, it will be fine. Times 1, 1, 1, 1, 1, 1, 1, 1, 1 times x1, x2, x3. So this will be theta times x lambda, lambda x1, lambda x2, lambda x3 plus gamma, or let's say lambda, whoops, times, so x1, x1, x1 plus x2 plus x2 plus x2 plus x3 plus x3 plus x3. Well, what does that now look like? It is lambda times x1 plus gamma times x1 plus x2 plus x3. And it is lambda times x2 plus gamma times x1 plus x2 plus x3. And lambda times x3 so the question now is, what is x1, what is x2, what is x3? Do they define what x is? Okay, if the set, okay. If the set is just numbers, okay? So then the set is x1, x2, x3. And what we then do mathematically is, okay, we weight all of the individual items of the set by a lambda, and then we add the combination of these values to that. Okay. And because this term here is permutation invariant, and this term depends on the input, we get permutation equivariance. That is, if we put x1, x2, x3 into the permutation equivariant layer, we get y1, y2, y3. And if we put x2, x1, x3, we get y2, y1, y3. Let's also just test this out. Let's hook up Python, or yeah, well, okay, import torch. Do I have torch here? Yes. Okay, let's say big theta is equal to torch.I. Is this possible? Yeah. And let's set m is equal to 16. Let's have 16 numbers. Theta is equal to torch.im. No. Lambda. Let's also define lambda as, or L 0.5 and gamma as 0.5. So it's just a linear interpolation. Theta is equal to torch.L times torch.im plus gamma times torch.ones m and torch.ones m t. Or maybe dot reshape 1 by 3 and reshape 3 by 1. And not 3 by 1, m and m. Oh. And now we have theta, which is this matrix. And now we have an x. Let's say x is equal np.arange, no, torch arange 16 or m. And let's do a matrix multiply with x. Oh shit. Expected scalar type float but found long. X.d type. Oh. D type torch.float. We get this. So let's quickly we get the output. Where do we put this? Let's go onto this and let's create a new terminal. Let's see. Let's just get this temporary file here. Let's copy this tensor. Let's put it here so that we can see all of the individual numbers. And let's say, okay, can we torch sort? Yes. Okay. Now we do the exact opposite. We say x prime is equal to torch dot sort torch.sort x and then descending true. X prime should now be 15, 14, okay. Oh no, we want like this. Okay. And what we now expect is that the new output is just the reverse of the input, because we had x, and if the layer is permutation equivariant, we should now get the exact opposite if we multiply it with theta. And we get this. Okay, let's record a macro. Oops. Okay, we go to the beginning of the line, search a comma, W, I this, and good. Now we go here. So 60, 60, 60.5, 60.5, 61, 61, 61.5, 61.5, 62, 62. Okay, 0.5. So we always have minus 0.5 here and always plus 0.5 here. So this is what they mean. All right. Yeah, so and probably lambda and gamma are learnable, I think. Are they learnable? I suppose they are the things that, Yeah, probably lambda and gamma can be learned. So yeah. I wonder what we could now do. Quickly. I wonder, do I now go offline or should we try to implement something? Okay, so maybe how the other thing works. So let's go here. Let's go. What? Am I still online? Did my stream break? I don't think so. Okay, let's open. No. How did this work again? Oh. Let's. I don't have a stream directory. Let's make one. And let's now open folder. Stream. Man. Okay, 5. Let's go here. Let's create a file. Deep sets.ipy notebook. Let's create a virtual environment here, maybe. Where's the terminal? VS Code. Hello? Okay. pip3 install torch. Oh no. You really have to download this? Man, I have it installed. Well, okay. Let's just try it. Well, this doesn't exist. So can you do this? Damn. Install? No. Oh no. Do you have to download this as well? Oh man, come on. If I do Python, I have Torch. I don't know how you do this, to be honest. Okay. All right. Well then, in the meantime, let's just do this. Okay, let's say we have some nodes, and let's say node dimensions, node feature dimensions is 10 or 16, and node hidden dimension is 64. Yeah, well, I'm I'm fine. I'm trying to implement something. Let's say, okay, our nodes is just torch. Oops. Torch dot. Is it torch random? Yeah. And it is okay. And nodes. Let's say we have 32 nodes. For each node, we have D features and D hidden. So we have 32 nodes with its features. Then we have some projection matrix. Torch dot rand n, and it projects the features into the hidden. And then we need our set layer. So let's say this is invariant theta is equal to D hidden torch.rand and D hidden. So this is executed for each node independently. And then we do a pooling. And the equivariant theta would be a little bit differently. It would be, we have L, let's say it's 0.5, and we have G for gamma, which also 0.5, or let's say torch.tensor. And it is L times torch.I but I think it's a little bit different. Does the stream still work? D hidden? No, D hidden, this is not correct, right? We need it to be different. Now each x is no longer a each x is no longer a single value, but it is a vector. Now, how do we do this? So the original equation was, this is n nodes, let's say num nodes, plus gamma times torch dot ones, and then num nodes. This was the original equation, but this doesn't work. Because we're now dealing with vectors. Each node is a vector. So this invariant deep set network would be, this should work. It would just be nodes at proj nodes. H nodes. Then we would do H nodes at, no, the invariant theta at H nodes. This is the, how do we call this? F nodes. And then we pool them together by, for example, summing them. I always get the dimension here wrong. This will be, so F nodes will be num nodes times D hidden. And what we want is just D hidden. So we want to sum across dimension 0. So this is the pooled representation. And then we perform an output. Then we get the output by multiplying it with another layer. So the equivariant deep set network works a little different. Now, okay, so proj nodes is num nodes D hidden. The output should be D out. Oh yeah. Invariant out. This will be D hidden and D out. Let's say D out is equal to 8. And here we just do, okay, out invariant out at wrong. This is the exact opposite. We have to transpose this, right? So nodes is num nodes the hidden at, so this will be num nodes the hidden. This will be num nodes this. And this will be pooled at, but we could have also transposed this, but okay. But what does it look like for the equivariant theta? We need d out, no, num nodes d out. So this should be then a matrix that, so equivariant theta no, this is also not correct, right? That's also not correct. But this is, okay, so this would have to be a d hidden d out. Okay, this downloading is way too slow. I will do this off stream. But okay, what would this look like for a vector? If x is if each and every one of them is now no longer, so if x1 is a vector, what does that change? How does this change the calculation? Does it change the calculation? Maybe even not. So let's say x11, x12, x13, x14. These are all the features of x1, x2, x3, and so on. This could work. But then we would have to transpose or do we? Okay, this is num nodes this is num nodes d out. Num nodes d out. What if num nodes the hidden? What if okay, equivariant theta is num nodes, num nodes. And then we just do, okay, we just do it anyways, right? And then we don't pool. I think this works out. So if this is a vector, let's make an example. Okay, so we have lambda, 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 0, 0, 0, 0, 0, 0, times x, which is x1, 1, x2, 1, x3, 1, x1, 2, x2, 2, x 3, 2, x3, 1, x3, 2, x3, 3. All right. Plus gamma times, oops, no, it's just gamma, 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 gamma. I have no idea how to properly do this. Times x1, 1, x2, 1, x3, 1, x1, 2, x1, 3, x2, 2, x2, 3, x3, 2, x3, 3. Okay, the first matrix multiply is then x1, 1. Yeah. Lambda times it's just lambda times x1, 1, x1, 2, x3, 1. What? 1, 3, 2, 3. Let's just call it big X. Plus this is now a little different. It is x1, 1 plus x gamma times we could also put it here. X2, 1 plus x3, 1 x11 plus x21 plus x31, x11 plus x21 plus x31. The second one is x12 plus x22 plus x32 repeated. And the third one is x13 plus x23 plus x33 repeated. So this is the mixing of the elements, and this is just the weighting. And permutation invariant. And this should work. Because I don't want to install Torch on the stream, because this will break my internet. I will do it on another day. So this is it for today. No, I'm at the moment not using Blue Sky. Yeah. I wish you a nice Sunday evening. Yeah, I'll see you on the next one. Bye.